Okay, so our last type of circuit is an RC circuit. An RC circuit is one that has a resistor along with a capacitor. So this is the symbol for capacitor, two parallel plates, just same length against each other. So on one side of the capacitor, it's going to develop a positive charge, and on the other side of the capacitor, it's going to develop a negative charge. And basically the function of this resistor is to kind of slow down the current so it doesn't go vroom and just automatically like burn out kind of your capacitor. So the current's going to go through the resistor and it's going to end up charging your capacitor. So remember, our capacitor, the charge on the capacitor is equal to the capacitance times the voltage, Q equals CV. And so what's going to happen is our capacitor is going to keep charging until the voltage on the capacitor is equal to the voltage of the battery. And then at that point, no more current will flow through the resistor. So there's some changing currents going on here. So how does the current change throughout this whole process? The current is really a function of time. So this really, if we were going to be all technically, this would be I of t. Okay, so I is a function of time, is equal to your initial current. This would be if it was just the current or just the battery and the resistor. So that would be our I naught. Our initial current. And then this is E. This is the exponential function. That's the inverse of ln. So e to the negative, this is our time, how long has passed. So how long has our circuit been hooked up. And this is the time constant, which is really the product of the resistance times the capacitance. So this two, when you multiply these two together, you actually get a time out of it. So RC is actually a time. And one of the really interesting properties of RC is if we look at this, so let's say that our time is one time constant. So we have RC over RC. That's e to the negative 1. Okay, e to the negative 1, if we do it on our calculator, the e button is an inverse function of the ln, so we go second ln e to the minus 1, and that comes out to 0.368. Okay, so basically this whole term here becomes, that's a number, 0.368. So what that tells us is that the current after one time constant at RC, whatever that is 36.8%, 0.368 times your initial current. So terms you want to look for are like 37%, 63%, because 37 and 63 is 100. So we can charge it or we can discharge it. And so it's going to be like 37% or 63%, and that's after one time constant. If we did two time constants, so that means the time is twice what the product of RC is. So 2 RC. Okay, so if we look at our equation, we have e to the negative 2 RC over RC. So the RC's cancel. So we have really e to the negative 2. So e to the negative 2 is 0.135. Okay, which will mean we're going to have 14% of our current left or 86% of our current. So this is after two time constants. And then the 37% and the 63% are after one time constant. So a lot of times what the questions will say is like this. So 14% is one of those magic numbers, and so our current is going to decrease, and 14% from the previous page is 2 time constants. Well, let's find out how big one time constant is. So the time constant is the product of your resistance times your current. So we have a 5 ohm resistor and 100 microfarads, so 100 times 10 to the minus 6 farads resistor or capacitor. So that's going to come out to 500 times 10 to the minus 6 seconds, or 500 microseconds. So that's one time constant. So if we multiply that by 2, because that's 2 time constants, we have 1,000 times 10 to the minus 6 seconds, which is 1 times 10 to the minus 3 seconds, which is 1 millisecond. So it'll take 1 millisecond, not very long, you won't see it, snap, for the current to dwindle down to 14%. So this one's going to charge up really quick. Most of the time in RC circuits, our resistances are bigger than the 5 ohms. We could, there's a whole bunch of things we could do with this. We could say, okay, now that we know what, there we go, it's not pinching. We could actually calculate what that current would be, but it would just be simple V equals IR. And we know the voltage. We know it's 10 volts. So we know it's 10 volts. We know it's 5 ohms. So that's a simple V equals IR. So our initial current, 10 volts, is equal to I times 5. So our current's going to be 2 amps. And we know we have 14% of that, so 14% of 2 amps is 0.27 amps. So that's how much current we had. We could also talk about the charge on the capacitor, because as the current is dwindling, the charge on the capacitor is getting bigger and bigger and bigger. Turns out that the total voltage, that's the voltage of the battery, is going to equal the voltage through your resistor plus the voltage through your capacitor. So when you add those together, you're going to get your battery's voltage. So this is a kind of a nice relationship, because as our resistor is getting smaller, our capacitor is getting bigger. And we have Q equals CV. Well, remember, C is the capacitance, so that's a constant. And if we know the voltage drop across the resistor, we can find the voltage drop across the capacitor. So we know V, and so we can calculate Q. And it turns out the relationship for Q is the same as the relationship for I, except for instead of it dwindling, it gets bigger. So we had the 36% and the 14%. Instead of using those numbers, we're going to use the bigger numbers, the 84% and the 63%. We're going to use those numbers instead, because the charge is equal to the initial charge times 1 minus. So it kind of depends on e to the negative t over rc. So it kind of depends on, are we making it bigger or are we making it smaller? This equation kind of looks confusing. You can use it, it's not wrong. But you need to say, okay, is it charging up or is it discharging? This is if it's charging up. If it is discharging, it would look like, discharging meaning the charge is leaking off the capacitor because it's hooked up. If it's discharging, then it looks just like our current one. So all of these are totally interrelated with each other, and they're different versions of the same thing. So go look at the solutions now on your pretest. Go look at the questions on your pretest. Look at the solutions, see how it works out. We'll see you tomorrow.